Quantum entanglement is often described as spooky action at a distance. Two particles are created together. They fly apart. Then, when one is measured, the other seems to respond instantly. To many people, this sounds like magic. It sounds like telepathy. It sounds like faster-than-light messaging. But that is not what entanglement is. You see, this fundamental misunderstanding has completely warped our perception of the quantum world, basically turning rigorous physics into science fiction. If we really want to understand the true nature of reality at this scale, we have to completely abandon the illusion of spooky messaging.
Entanglement is not spooky messaging. It is deeply shared persistence.
So let's dive into the standard reality of quantum mechanics to see what's actually happening here.
To understand the reality, we really must discard that popular myth. In standard quantum mechanics, two systems can be described by a single, joint quantum state. Even if these particles are literally separated by entire galaxies, their measurement outcomes remain correlated. But we must be incredibly careful here. This does not mean one particle sends a usable signal to the other. It doesn't allow for faster-than-light communication at all. What it actually means is that these two particles just cannot be fully described as independent systems. Their possible outcomes belong to one shared mathematical state. When we try to treat them as entirely separate entities, we're really just projecting our everyday classical biases onto a framework that operates under entirely different laws of coherence.
Now, let's reframe this using general emergence mechanics, or GEM, to give this process a concrete visual logic.
Stop picturing entangled particles as two little marbles connected by an invisible string. That picture's misleading. Instead, picture two local expressions of one shared coherence geometry. In GEM, we aren't replacing the underlying quantum mathematics. Instead, we're giving it an unyielding visual logic. We call this an admissibility basin. Basically, it's a region of possible states that can remain coherent together. The weirdness of quantum mechanics really only begins when we try to ask isolated object questions about what is fundamentally a shared state geometry. Our confusion stems from mistaking the visible peaks of a wave for the entirety of the mathematical structure itself.
They are separated in space, but not fully separate in state. Think of the classic analogy of a pair of gloves. If you send a right glove to Mars and a left glove to Earth, opening the box on Earth instantly tells you what's in the box on Mars. But quantum entanglement isn't merely classical hidden information. A much better image to hold in your mind is a single musical chord stretched across space. The notes might be far apart, sure, but they belong to one harmonic structure. The moment you measure one note, the allowed relation of the entire chord is fixed. The structure persists seamlessly, totally unbound by the physical distance between its localized expressions.
This leads us directly to the profound nature of a single rulebook, or shared constraint.
When two particles are entangled, their outcomes are not independently selected from two separate menus. They are highly constrained by one shared menu. The outcome simply must fit the global geometry of the whole entangled state. The two peaks of our geometric wave have to shift in perfect counterbalance. There's zero individual agency for a single particle in this state. Every possible measurement outcome is dictated by the overarching geometry that binds them together. It's really a symphony of mathematical precision where neither particle ever acts alone.
Entangled particles do not carry private answers. They share a single rulebook.
Okay, so let's completely demystify the actual act of measurement and how it interacts with this shared geometry. Consider the physical process of measurement, which is a phenomenon historically shrouded in, frankly, unnecessary mystery. In standard language, measurement collapses the wave function. But let's view this purely through the lens of geometry and constraint. When one particle is measured, the measuring apparatus physically couples to the system as a constraint node. Measurement is absolutely not just passive looking. This physical coupling actively changes the local boundary conditions. And under that profound boundary pressure, the shared admissibility structure, that shared basin, is forced into one actualized branch. The result on one side is correlated with the result on the other simply because both belong to the exact same joint geometry. Collapse isn't a signal traveling between particles. It is the immediate resolution of a structural tension.
Measurement does not send a message. It resolves a shared geometry.
This brings us to a point requiring absolute scientific caution. No signal is permitted here.
The person measuring one particle absolutely cannot choose or dictate the result in a way that transmits information. Information transfer remains strictly scale-bound by the speed of light. It's an immutable law of our observable universe. Even if the state resolves instantly across vast cosmic distances, no controllable message can be sent from one observer to the other.
It's only when both observers later compare their logs through ordinary, slower-than-light communication that the profound correlations become visible. Only then will the data reveal an undeniable synchronization, proving the two particles were governed by the same overarching state. Ultimately, entanglement gives us correlation without communication.
Entanglement is essentially quantum-scale evidence that separateness just isn't always the deepest description of nature. In GEM, many systems persist simply because parts remain linked inside one coherence basin. Think about it. A molecule is not just a collection of disconnected atoms, it's a shared bonding geometry. A cell isn't just a loose association of molecules, it's a bounded gradient system. And an entangled pair is not just two particles separated by the void, it is a shared quantum state. We look at different scales and we apply different mathematics, but we are ultimately asking the exact same deeper question: what can remain coherent as one system? Reality is not only made of things, it is made of admissible relations.
So it's clearly not magic communication. It's not a hidden radio signal moving faster than light. The particles might look completely separate to our limited macroscopic senses, but the state is fundamentally, mathematically one. As we reconsider our place within such a deeply interconnected universe, we really have to shed the biases of classical isolation. So I'll leave you with this final thought. Are entangled particles communicating across space, or are they simply two visible edges of one deeper coherent state?